The impact happened in the dark. On October 8, 1962, the operator of a suction dredge working the Weser River felt his machinery jam. The heavy industrial pumps were designed to inhale thousands of tons of river silt to expand the shipping lane for modern steel freighters. They were not designed to process solid oak. When the crew halted the intake to clear the obstruction, they did not find a submerged log or a lost anchor. They found a complex arrangement of heavy timber, black as coal and hard as stone. The dredge had not just struck an obstacle, it had collided with the late Middle Ages. The location was the heart of the Bremen harbor district in Germany, in the Weser near Reassembling. This was an active construction zone driven by the economic demands of the 20th century. The water was turbid, moving fast with the tide, and completely opaque. Visibility at the bottom was effectively zero. The engineers on the surface faced an immediate decision. If this was merely old debris, the standard procedure was to break it up and pump it out. Time was expensive, but the fragment surfacing in the intake filters told a different story. The wood was oak, and it showed the distinct tool marks of heavy adzes used by shipwrights long before the invention of the steam engine. This accidental collision revealed the central paradox of wet salvage. The same environment that hid the vessel was the only reason it still existed. For 6 centuries, the hull lay locked under dense sand and silt, in a sealed, low-oxygen pocket where decay could barely function. The ship survived not because oak is immortal, but because the organisms that consume wood were starved and slowed to a crawl. The discovery immediately shifted the operational logic from construction to crisis management. The dredging team had unknowingly breached the seal. By exposing the timber to the river current, they had reintroduced the threat of erosion. More dangerously, they had exposed the artifact to the possibility of extraction. The wood looked solid to the naked eye. It retained its shape, its grain, and its volume. But this solidity was an illusion maintained by the water itself. Over 6 centuries, the oak's cellular structure had transformed. What looked like solid timber was no longer wood in the structural sense, but water-saturated material whose mass came as much from what it held as from what it was. The dredge operators were right to call it immovable. The hull's apparent strength and weight were largely the weight of the water that had swollen and stabilized it. The local authorities paused the harbor expansion. This was a decision of significant financial consequence, halting a major infrastructure project for the sake of an unverified wooden obstruction. Divers were sent down to inspect the contact zone. They worked by touch in the freezing current, feeling their way along the serrated edges where the dredge had chewed into the hull. They reported a continuous structure, listing heavily, buried deep in the riverbank. It became clear that this was not a fragment. It was a cohesive hull, potentially intact. The sheer size of the anomaly presented a physics problem. A lifting operation for a steel ship involves welding patches and pumping air. A lifting operation for a wooden ship in this condition involves calculating the failure point of a wet biscuit. The structural integrity of the hull was almost zero. Any attempt to pass lifting straps under the keel would slice through the softened wood like a wire through cheese. The salvage engineers realized they were not looking at a recovery mission. They were looking at a forensic intervention. The ship could not be lifted, it could not be towed, and it could not be left where it was, or the current and the dredge would destroy it. The only option was to change the environment around the ship completely. They had to carve out a controlled pocket of stillness inside a moving river. The engineering team faced a contradiction. To save the structure, they would have to dismantle it. The oak timbers were no longer rigid beams capable of bearing a lift, so the recovery could not be a conventional salvage operation. It had to become something closer to controlled excavation. This fragility is driven by the mechanics of cellular collapse. In fresh timber, the strength comes from the cellulose that forms the thick walls of the wood cells. But after centuries of immersion, even in the protective mud, the cellulose degrades. The cell walls thin out until they are mere membranes. The only force keeping the wood expanded in its original shape is the water trapped inside it. This water acts as a structural filler. If that internal pressure is removed, or if the wood is subjected to the crushing force of gravity without support, the cells flatten. The wood does not just break, it shrinks and distorts, losing its geometric memory. The decision was made to disassemble the ship underwater, component by component. This required a level of precision that scuba divers operating in zero visibility silt could not provide. The solution was a piece of heavy industrial hardware known as a diving bell vessel. The diving bell is a massive steel caisson, open at the bottom, suspended from a surface support ship. It does not seal against the riverbed mechanically. Instead, it uses gas laws to create a workspace. Giant compressors on the surface pump air into the caisson until the internal air pressure exactly matches the hydrostatic pressure of the river water at that depth. This equilibrium pushes the water level down, exposing the riverbed inside the bell while the surrounding water is held back by a wall of air. Inside this pressurized steel room, the environment is surreal. The salvage crew did not swim. They worked on the muddy river bottom in a compressed atmosphere, moving and seeing as if the river had been pushed away. While strict pressure discipline governed every shift back to the surface, the only reminder of the hostile environment outside was the open pool of water at their feet, the gateway back up. Over the next 3 years, the recovery unfolded in campaigns as the team measured, lifted, and chased scattered timbers. The diving bell vessel, Karl Straat, was brought in to reach the widely dispersed parts, turning the work into reverse engineering of a medieval build. They had to locate iron nails fused to wood, loosen joints without shattering softened timber, and catalog every fragment, an excavation performed in a high-pressure atmosphere. The scale of the fragmentation was immense. The hull was not a single object anymore. It was a collection of more than 2,000 individual timbers. Each piece had to be mapped, tagged, and carefully passed out of the diving bell into wet storage tanks. The total weight of the recovered material was almost 45 tons. This mass represented a logistical nightmare. The moment a timber left the pressurized protection of the bell, it had to be kept submerged. If the wood dried for even a few hours, the water supporting the cells would evaporate, and the irreversible process of cellular collapse would begin. The diving bell allowed the team to recover the ship without destroying it, but it also created a massive jigsaw puzzle. The vessel had been reduced to a warehouse full of wet, black lumber, thousands of pieces that had to become a hull again. With the recovered timber secured in water tanks, the operation shifted from physical recovery to forensic interrogation. The black oak fragments were not just a structural puzzle, but a biological archive, and the team needed to determine exactly when the vessel was built. They turned to Dendrochronology. This method relies on the biological fact that trees do not grow at a constant rate. In years with high rainfall and favorable temperatures, a tree produces a wide growth ring. In years of drought or extreme cold, the ring is narrow. Over the lifespan of a centennial oak, these fluctuating widths create a unique pattern, a sequence of wide and narrow bands that acts exactly like a fingerprint or a barcode. Because the climate affects all trees in a region simultaneously, this pattern can be matched against a master chronology of known timber samples. When the researchers analyzed the cross-sections of the recovered hull planks, the sequence was unmistakable. The oak trees used to build the ship had been felled in the winter of 1378 to 79, placing construction around 1380. This date was a revelation. It placed the vessel squarely in the height of the Hanseatic League, the powerful commercial alliance that dominated trade in the North Sea and the Baltic. Until this moment, the design of a Hanseatic cog was known mostly from crude illustrations on city seals and scattered references in documents. Now, historians had a physical reality, complete enough to test the old drawings against real timber. The dimensions of the recovered components allowed the engineers to extrapolate the full size of the ship. It measured approximately 76 feet in length with a beam of 25 feet. This was a massive cargo carrier for its era, a floating warehouse designed to move bulk goods like grain, timber, and fish. But the forensic analysis revealed a contradiction. A ship of this size should have been packed with artifacts of its crew, coins, weapons, galley pottery, and personal effects. Instead, the recovery produced surprisingly little of that everyday clutter, with only a handful of finds like a lone leather shoe and a few fittings recovered alongside the timbers. The absence of crew equipment pointed to a specific operational status, but the positive proof came from a different class of artifact found trapped within the hull. The divers had recovered a specific set of iron tools, a heavy shipwright's adze, augers for drilling peg holes, and chisels. These were not the tools of sailors used for emergency repairs. These were the heavy industrial tools of the builders. The location of these tools, combined with the lack of ballast stones and the scarcity of personal gear, solved the mystery of the loss. This was not a shipwreck in the traditional sense. It was a construction site accident. The evidence suggests the ship was still on or near the slipway, nearing completion, when a storm flood struck the shipyard. Light and unfinished without ballast, the hull was lifted off its supports and swept into the river. It drifted downstream and sank before it ever carried a single pound of paying cargo. This diagnosis changed the reconstruction strategy. The team was not rebuilding a ship that had been worn down by decades of service. They were rebuilding a brand new vessel that had never sailed. The timber edges were sharp, the joints were tight. The damage was limited to the trauma of the sinking and the dismantling. However, knowing the shape of the ship and the date of its birth did not solve the problem of physics. The team now had to take 2,000 soft, warped pieces of wood and force them back into the shape of a 76-foot hull, all while fighting the inevitable distortion of drying timber. The forensic phase was over. The structural crisis was about to begin. The reconstruction of the Bremen Cog presented a geometry trap that no modern naval architect had ever faced. The team possessed the original components, but the material properties of those components had been corrupted by 6 centuries of immersion. The oak planks were warped, swollen, and devoid of mechanical stiffness. If the engineers simply stacked the 2,000 timber fragments on top of one another, the weight of the upper hull would crush the lower sections into a shapeless mass of pulp. This problem was compounded by the specific engineering lineage of the vessel. The cog was built using a technique known as shell-first construction. In modern shipbuilding, and indeed in most shipbuilding after the 15th century, the process begins with a rigid internal skeleton of ribs and frames. The outer skin is then nailed to this frame. The frame dictates the shape, and the skin merely seals it. The medieval shipwrights worked in reverse. They built the outer shell of the hull first, overlapping the oak planks in a style called clinker construction. The planks were riveted together at the edges, creating a cohesive, tensioned skin that supported itself. The internal framing was inserted only after the hull form was complete. This meant the strength of the ship relied entirely on the precise curvature and tension of the planking. For the museum team, this meant they could not build a jig and force the wood to conform to it. They had to coax the softened, distorted planks back into their original alignment piece by piece, without any structural spine to guide them. The solution was to treat the ship not as a construction project, but as a suspension bridge. Inside the museum hall, a massive steel gantry was erected over the reconstruction site. Instead of building the ship from the floor up, the engineers decided to hang it from the ceiling down. This system utilized a dense array of adjustable steel rods. The most fragile timbers were supported individually from the gantry, so their positions could be tuned in 3-dimensional space without loading the wood below. This allowed the conservators to position a plank in 3-dimensional space, adjusting its angle and elevation by fractions of an inch, without placing any weight on the timber below it. The hull was reassembled like a giant marionette. The weight of every single board was transferred to the steel overhead. This neutralized the threat of cellular collapse during the assembly phase. The soft wood floated in the air, held in formation by the tension of the rods rather than the strength of the joinery. This process required a disciplined environment. The reconstruction hull had to be held at near saturation humidity, with sprinkler systems running constantly, not as a convenience but as a life support measure. The workers wore rain gear indoors, handling heavy, sodden oak, while water dripped from the ceiling and the hull itself. Slowly, the ghost of the ship appeared. The overlapping clinker planks were realigned, and where original fastenings had failed or could not be reused, conservators introduced selective, documented fixings, often wooden dowels, only where stability demanded it. The gaps were consistent. The complex curves of the bow and stern, lost when the ship was flattened by the river sediment, were recaptured by the adjustable suspension system. By the end of the reconstruction phase, the ship stood complete for the first time since 1380, massive and imposing. But it was also a kind of deception. The hull held its form only because a steel forest surrounded it and water still filled its cells, a sculpture stable only as long as it stayed wet. To make it permanent, the water had to be removed, and that meant the next battle would not be fought with cranes and rods. The reassembled hull standing in the museum hall represented a victory of geometry, but it remained a prisoner of chemistry. The ship was still 100% waterlogged. The moment the sprinkler systems were turned off, The water supporting the cellular structure would evaporate, and the wood would shrink, crack, and eventually disintegrate into dust. The engineers faced a lethal trade-off. They could not keep the ship wet forever, as biological decay would eventually restart, but they could not let it dry out. They needed a way to remove the water without removing the structural support it provided. The solution was to replace the water with a substance that would remain solid at room temperature. The chemical chosen for this exchange was polyethylene glycol. Polyethylene glycol, PEG, is a synthetic wax-like polymer with a useful trick. It dissolves in water, and as the water leaves, the polymer remains as a solid support. The theory of the conservation was diffusion. If the waterlogged timber was submerged in a heated solution of this polymer, the molecules would slowly migrate into the wood and replace much of the water inside the weakened cells. When the process was complete, the remaining water could be removed with far less shrinkage because the PEG left behind a stabilizing scaffold within the timber's compromised structure. To execute this, the museum did not move the ship to a tank. They built a tank around the ship. A massive steel container rose inside the main hull, encapsulating the entire hull. Ship in a bottle, except the bottle was an industrial vat holding on the order of 800,000 liters of solution. The critical variable in this operation was time. The oak planks of the cog were thick, and the diffusion process answers to physics, not the schedule of a museum. You cannot rush the treatment without risking damage to fragile cells. It has to seep in slowly. The engineers estimated roughly 18 to 20 years for the solution to reach the core of the thickest timbers. The ship disappeared from view. It sat submerged in dark, heated liquid while pumps circulated the solution to keep concentrations even. Progress measured in millimeters of penetration per year. During this immersion, the hull relied on hydrostatic suspension. The buoyancy of the chemical fluid helped carry the weight of the waterlogged wood, working in tandem with the steel rods to prevent collapse while the timber was still soft. The concentration of the wax was increased incrementally, year after year. It started as a mostly water mixture and ended as a concentrated sludge. The process required absolute patience. If they drained the tank too early, the core of the timber would still contain water. That water would eventually evaporate, causing the center of the planks to shrink while the outside remained fixed, tearing the ship apart from the inside out. Finally, in the year 2000, the saturation targets were hit. The pumps were reversed. The liquid level in the tank began to drop, revealing the hull inch by inch. The wood that emerged was no longer the soft, spongy material that had come out of the river. It was dark, heavy, and far less prone to sudden collapse. The tank walls were cut away, and the suspension rods were detached one by one. For the first time since the dredge struck it in 1962, the Bremen Cog could be shown freestanding, then carefully monitored, and as needed, discreetly supported as slow deformation continued. If the Bremen Cog were discovered today, the operational decision might be different. Modern marine archaeology relies heavily on non-invasive survey tools, sonar, photogrammetry, and sub-bottom profiling, to build a high-resolution digital model of what lies under the sediment, sometimes down to sub-centimeter detail in ideal conditions. This approach reduces the need for risky lifting. It preserves the site, but it leaves the reality buried in the mud. The salvage of 1962 was performed at the limits of mechanical capability, but it delivered something a digital model can never fully replace. It delivered the mass and the presence of the object itself. The vessel that stands today in the German Maritime Museum is the physical definition of a missing link. Before its recovery, the Hanseatic Cog was a ghost of naval history. It existed only in the crude, two-dimensional caricatures stamped on medieval wax seals or in the margins of tax ledgers. Historians knew these ships carried the trade of Northern Europe, but they did not know how they were built. The recovery of the Bremen Cog converted academic theories into hard engineering data. It proved that the cog was not just a clumsy barge, but a sophisticated synthesis of Viking design principles and heavy cargo capacity. The ship is now a stable structure, but it is no longer purely organic. The 18-year chemical process has transmuted the hull into a composite material. The oak timber acts as a scaffold for the synthetic wax that now occupies its cellular space. This waxy stabilizer allows the 76-foot hull to support its own weight without the steel suspension rods that once filled the hull. The ship stands on its keel, tilting slightly to the side, held in that pose by discrete supports, an orientation shaped by burial, recovery, and conservation, not a perfect snapshot of the riverbed. However, this stability is not absolute. The preservation did not make the ship immortal, it merely slowed the clock. The museum hall is a sealed environment, a life support system for the artifact. The humidity and temperature are rigorously controlled to prevent the wax from migrating or the remaining wood fibers from reacting to the atmosphere. The ship has survived the river and the chemical bath, but it remains vulnerable to the slow, relentless friction of the air itself. The Bremen Cog survived for one reason that feels almost unfair. It was lost before it could ever live. Had it been finished in 1380, it would have sailed for 20 or 30 years, battered, repaired, refitted, and eventually broken up for firewood or eaten by shipworms. Instead, it went down as a brand new hull before it could carry a single paying load and was sealed away in a pristine state of incompleteness. The tools left behind remain the most poignant evidence of that interrupted timeline. They are not artifacts of a tragedy involving lost lives, but proof of a bad day at work that became a time capsule. The shipwrights lost their tools and their hull, but the future gained a perfect specimen. The salvage operation that began with a dredge collision in the dark water of the Weser River achieved a rare absolute success. It took a pile of 2,000 waterlogged fragments and reversed the entropy of 6 centuries. The Bremen Cog was built to sail the trade routes of the Middle Ages. It never made that voyage. Instead, it crossed a much wider gap, sailing through the chemistry of preservation to deliver the Middle Ages to us.